Today's lesson is on stellar evolution, and this can get kind of confusing, so just make sure you follow along as best you can, and we'll go over quite a bit again in class. Stellar evolution just means basically the life cycle of a star. So it just doesn't start off as a star, it was something before, and it's going to be something after. Stars exist for billions of years, so astronomers have not been able to study a single star through its entire lifetime to see how it evolves. What they have to do is look at stars that they think are in different places in their evolution and then put the pieces together. So what we're telling you is our best guess. It's our best theory as to what happens with stars as they evolve over time. It can certainly be wrong. It keeps changing over and over again, and it's gotten complicated. As you see from this picture, there are many possible tracks now that we think a star might go through as it evolves from its start as a nebula to its final result. We're going to try to make it simple, and we're just going to do two paths. So we're going to say there's two options. Well, realistically, there are more. The two paths we're going to do low mass one. The path that we're going to take is this one. Okay, so basically it's the path we think our sun is taking. Then the high mass path we're going to take is kind of like this. Okay, we're going to take kind of a really high mass one. And like I said, just realize that many other things can happen along the way. This is our best guess now as to what happens, and it can certainly change in the future. And again, it's kind of our tracks that we're going to be following. We're going to do a low mass track, and then we're going to do a high mass track. So we're starting with the low mass track. The first step in developing a low mass star is a nebula. A nebula is just a large cloud of gas and dust, mostly hydrogen, a little bit of helium, a little bit of other gases. There's very weak gravitational attraction in the cloud, but there's enough that these pieces start to come together, and then they have more gravity, so more comes in, more gravity, more comes in, and eventually this cloud starts to contract, and as it starts to contract, it starts to spin. This is a picture of the Orion Nebula, so hopefully you've been seeing the constellation Orion in the night sky. You know that he has a belt of 3 stars across, and then hanging from his belt is a scabbard that he has his little sword that he puts in. This is there. If you look really closely, just with your naked eyes, it'll look kind of like a fuzzy star, or with some binoculars, you'll see kind of a fuzzy star. With a telescope, you zoom in on that fuzzy star, and you see it's not actually a star, it's a nebula that's forming stars, and you see 5 main ones that are forming and lighting up this nebula. Okay, so the first stage, big cloud of gas and dust, the nebula. That nebula continues to spin, and as it spins, the nebula flattens into a disk, and we now call it a protostar. Pressure and collision of solid matter inside the protostar causes the temperature to increase. After several million years of contraction, it gets to be about 10 million degrees Celsius. That 10 million degrees Celsius, that's the key, all right, one of the key points in the formation of the star. Once it reaches that temperature, it can then be considered a star. Because at 10 million degrees, that's when nuclear fusion begins. So hydrogen molecules fuse into helium molecules, and it gives off tons of energy. Some of the energy is visible. That's the light that we see. So it's basically the stars, it starts shining at this stage. So this is what we consider the star stage. A nebula might not just contract into a single star, it might produce several that revolve around each other. You can see this is a picture of binary stars that go around each other. And we'll have an astronomy project that will talk about those. You might also get planets produced in the nebula and start to revolve around the star. That's how our solar system formed. Okay, so there wasn't enough mass for our planets to form into more stars. They just became planets. So we ended up having 1 star in our solar system and 8 planets, or maybe 9, whatever you agree with. I'm not going to go much into fusion because the Sun project is going to talk more about fusion. Basically, the idea though is we have some protons. There's such intense heat and pressure, they smash together, and it forms a proton-neutron, a hydrogen atom. Then we're going to have the hydrogen atoms come together, so and it gives lots of energy. The hydrogen atoms then smash together and make a helium atom. So helium, 2 protons and 1 neutron, helium-3. Then 2 of those helium-3s smash together, they fuse, and they become helium-4. So 2 protons, 2 neutrons, and then lots of energy, and 2 protons fly out to start this chain reaction over again. So this is going to keep on fusing, 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 producing lots and lots of energy. This is what we're trying to do on Earth, trying to make fusion reactors to kind of solve the world's energy problems. We have fission reactors, we have some fission bombs, we have a little bit of fusion bombs too as weapons, and we can talk more about that. But really we want to do fusion. Fusion is kind of a clean way that we could produce lots and lots of energy. And it's self-sustaining. So fusion continues for a long time. The star doesn't expand though as this fusion goes on because gravity balances it out. Okay, and we're still in the stage 3 main sequence star. That's going to happen for billions of years. But fusion is going to stop when the hydrogen is used up. Gravity then causes the star to contract. That increases the temperature, so now helium can fuse into carbon. And then hydrogen fusion continues in a shell outside the core. That combined fusion causes the star to greatly expand and cool. Okay, so kind of make it simple, we have our star, it's fusing hydrogen, starts running out of hydrogen, it collapses into a small thing. When it collapses, it heats up. Now it can start fusing helium into carbon, and it expands. So we have the helium fusing to carbon in the center, and the hydrogen to helium outside. This we think is the future of our sun. We think when this happens, and it's a long way out, we think maybe it's another 4 to 5 billion years until this will happen. But our sun will contract, get hotter, and our sun right now is this size, and expand as it turns into a giant. It'll expand so far that it will engulf Mercury. Venus and the Earth will obviously be a lot closer, so that will mean some not so good things for us. But again, it's a long, long time in the future, and the Sun Project will talk more about that when they do their astronomy project. Stellar winds sometimes propel the outer shell of the giant, so we're still kind of the giant, and then the solar winds can propel some of that outer shell to create a planetary nebula. It's badly named. Astronomers used to think that this is where planets form, so they called it a planetary nebula. It's not now, we know, but the name is stuck. These planetary nebulae are fairly short-lived astronomically, about 1,000 years, but they are important because they project elements further out in the universe, which can then lead to more stellar evolution. We're in the next stage now, and it's going to become a white dwarf. So when the helium fusion in the giant ends, so the helium to carbon ends, gravity causes the last of the matter to collapse inward, and you're left with a hot, dense core of matter, which is a white dwarf. 1 teaspoon of a white dwarf would weigh 5 tons. And this picture shows you how big a white dwarf might be compared to the Earth. Okay, so kind of just a real quick recap. We had our sun, or our star, runs out of hydrogen, collapses, gets hotter, so now it can fuse carbon, so it gets really big into a giant, runs out of helium, so now it's going to collapse into this hot, dense core called a white dwarf. That white dwarf is going to shine for billions of years before it cools completely and becomes a black dwarf. And there are some other options in there. Instead of white dwarfs, there's things like red dwarfs and brown dwarfs stuff too. We don't think any black dwarfs exist yet because we don't think the universe is old enough to have any black dwarfs. So that'd be a future. Not all white dwarfs just cool and die calmly. Some of them have explosions that release gas and dust into space. Those explosions are called novas. The nova may appear to be 1 million times brighter than the star. Quickly, within a few days, the nova fades back to its normal brightness. Okay, so we have our white dwarf. As it cools to a black dwarf, you might have these little explosions, not that little, but you have these explosions called novas. And you can see in a picture here, this nova is going to shoot out, and then it's going to go back to being what it was. Okay, that was the last part for the low mass. So when we go back and look at our picture, we started off with the nebula. That changed into a protostar, so the nebula contracted and started to spin into a protostar. Protostar continued to contract and heat until it got to 10 million degrees. When it got to 10 million degrees, it turned into a star, a main sequence star. It was fusing hydrogen into helium. Runs out of hydrogen, it contracts, gets hotter, and then expands into a red giant. And it's fusing helium into carbon. It's going to run out of helium, or as it's doing that, you might have a planetary nebula get blown off. It's going to run out of helium. It's going to contract again into a hot, dense core called a white dwarf. That white dwarf might nova with little explosions as it cools to a black dwarf. Okay? So hopefully you can get your picture at the top there labeled with all the different steps as it goes through. We're going to save the high mass stars for the next screencast, so I'll end this one here.